Coulomb's law. Right? See, now we know how the charges are actually created. Right? So if those charges that are created are given to you, how are those two objects, how are the charged objects going to interact among themselves? When I use the word interact, I'm trying to say how are they going to exert the force on each other. Right? See, logically tell me, if I have a positive charge here and another positive charge here, which are separated at a reasonably decent distance, where they can interact with each other. Meaning of it, this one can exert a force on the other and the vice versa. Right? We suppose they both, let's say, are separated by a distance r. And let me say that the charges on these materials are Q1 and Q2 in terms of magnitude. So in this example, I took both to be positive charge, not necessary that both are supposed to be only positive charge. You can always take a combination. It can be both negative or positive and negative. Right? This is just a small consideration. Right? Now tell me, what will happen to this kind of a system? The first will exert a force on the other, and the second will exert a force on the first. Right? If I name them as 1 and 2, right? Can I see that in this scenario? Can I say there will be a force of repulsion that is acting because both are like charges, right? So the question is, repulsion and attraction are another term for push or pull. So what do you mean by repulsive? Repulsive is pushing away. Attractive is pulling towards each other, right? So in this case, what will happen? Repulsion is going to happen. Now the next question is, force is a vector quantity, right? So it is our job to give a proper direction to this. How do we define it? So how is the force going to act among both? So this charge is going to experience a force. Am I right? So in which direction will it experience? Will it experience in the rightward direction or in this side or this side? Rightward. So when I say rightward, we can experience a force in this way, which I call it as first option. It could experience a force in this way, which I call it as second option. It could experience a force in this way, which I call it as third option. So out of all these options, which one is the right? Why? Axis. Along the line. Correct. So force always acts along the line joining both the charges. So this and this are wrong. So this is the direction in which force is experienced due to whom? Force is experienced by the second charge due to the first charge. So I need to give a small subscript to it. What I do is I'll write it as F21. Are you able to understand the notation? So what is it? It is F21, right? Similarly, in this case, I think it is understood that the force experienced by first charge will be in the leftward direction, and it will be F. Right. So I need to give a name to this notation. Right? How do I write it? I'll say F21 is a force experienced by second due to first. What about F12? Force experienced by 1 due to or first due to second. See, there is one way of understanding where they might confuse you. Okay. One is F21 is there. They can say force experienced by second due to 1 or force exerted by 1 on 2. Both mean the same. So how much is the force? The first particle is exerting on the second. Right? I hope it is clear till this step. Right. Now comes an important question. We understood everything in terms of direction and everything. Now we need to understand what this Coulomb's law has to say, for which the first part I am going to concentrate upon is the scalar form. I'll concentrate on the scalar form. So what do I mean by scalar form is, I'll only be concerned about what is the magnitude of the force that is going to act when these two charges are going to interact with each other. The first point to be noted here is, Coulomb's law is applicable only for point charges. So what do I mean by point charge? Yes. So if you take the size of the charge, which is very small compared to the distance of separation between them, you call those kind of charges as point charges, or you can also call them as particle charges. Both mean the same. So point charge literally doesn't mean a point, its size is negligible. Okay. So you have a point charge. So when 2 point charges, this is the first point to be noted. When 2 point charges are, okay, right, when 2 point charges, only thing is I can't erase it. When 2 point charges Q1 and Q2 are separated by a distance R, then the force of attraction or repulsion between them, PW is between, okay, between them is observed to be first directly proportional to the magnitude of the charges. And second, inversely proportional to the square of the distance of separation. I hope it's clear to this. Yeah, directly proportional to the product of magnitude of either of magnitude of the charges, and inversely proportional to the square of the distance of separation. Am I clear to this? No. So if you are done with this, can I go to the next slide?
1 minute, sir.
So let me know once you are done. Done. So yeah. Shall we see the mathematical part of this? Right. So we wrote it in a theoretical form. Let's see the mathematical form. So it's obvious, right? The force of attraction or repulsion. So here, when I say this force, this is the electrostatic force, right? It's observed to be directly proportional to the product of magnitude of charges, right? And it is observed to be inversely proportional to the square of the distance of separation between them. So if obviously if I combine these, right? If I combine these two, what will I get? F is observed to be directly proportional to magnitude of Q1 into magnitude of Q2 divided by R square. So when I remove the proportionality symbol, what am I supposed to do? So you need to introduce a constant which is written as K into magnitude Q2, the whole divided by R square, which implies F will be equal to, this K is observed to be something like this, 1 divided by 4 pi, the symbol is called as epsilon naught. Okay, epsilon with a circular name bottom. It's called epsilon naught. Okay, it's not denoting. Okay, into magnitude of Q1 into magnitude of Q2 divided by R square, where this term is called as permittivity of free space. So it's called permittivity of free space, and this 1 divided by 4 pi epsilon naught has a value of 9 into 10 power 9. I want the units. How did you get it? Just rearrange it. So it's going to be Newton meter square per coulomb square. I hope everybody understood. This is Newton. This is 1 by 4 pi epsilon naught. R square will come this side. So Newton meter square, this will come to the denominator. It is right. Now, if I rearrange this equation and try to find the value of epsilon naught, it comes out to be 8.85 into 10 power minus 12. What will be the unit? We'll see that. I was about to ask you that question. Okay. So let's see. So epsilon naught is 8.85 to 10 power minus 12 unit. It's a reverse. It's Coulomb square by Newton meters. Okay. So to answer your question, Coulomb's law is applicable when you have two charges. If it crosses that, we need to use some mathematical operation, which I'll tell you later. Now tell me, what is the form in which we have written this? I gave you the bracket. What is it? It's the scalar form. Why are we calling it a scalar form? Because I told you in the beginning of the discussion itself, force is a vector. Till now, we took the direction into consideration, but we didn't try to write it in the vector form. Right? We understood what is F21 and F12. But here we wrote only the value of the force experienced by either of the charges. You can ask yourself, what is this F? Is this the value of F21 or F12? No, it is the magnitude of both. Both F21 and F12, though the directions are different, their magnitude is this value. Right? So this is the scalar form. So this gives space to the next question. Is there something called a vector form? So obviously we need to have a counterpart for it. Right?